Hi everyone, so today we're going to continue on with chapter 11. So this will be the last chapter that we are covering in Organic 1. So this material is going to go along well with chapter 10. So in chapter 11, what we're going to be talking about is reactions of alcohols. So first we're going to talk about the oxidation and reduction in organic chemistry. So just a few terms to go over. When we have reduction, it's going to mean that we have the either addition of hydrogen to a pi bond, or we have the loss of oxygen or loss of a halogen. When we look at oxidation, so oxidation is going to be the removal of H2. So a lot of times we'll see the creation of a pi bond. It's going to be either addition of an oxygen or addition of a halogen. So let's look at a few examples of those terms. So looking at examples, if we start here with A and we go to compound B, so going from A to B, this is going to be an oxidation process because we again are creating that pi bond in B. If we were to go from B to A, so now we're removing that pi bond, so that would be a reduction process. If we go from B to C, this is actually going to be an oxidation process because we have the addition of an oxygen. So again, addition of an oxygen is going to be an oxidation process. If we go from C to D, so going from C to D is actually going to be also an oxidation process. And the reason for this is so remember when we did thinking about priorities, we were thinking about like breaking and duplicating the bond. That's really the way you want to think about these types of processes too when you're looking if it's oxidation or reduction. So what we would have here is something that we could think of like this. So now we're going from one oxygen to two oxygens. So that would be an oxidation process. If we were to go from D to C, so we're going from D having two oxygens to C having one oxygen, so we're removing one of those or loss of an oxygen, so that would be a reduction process. If we're going from D to A, so again, this would also be a reduction process just because we have the loss of oxygen. So let's look at some oxidation states of oxygen-containing compounds. So what the oxidation state really tells us, it's going to describe the degree of oxidation. So oxidation involves an increase in oxidation state. So if we start off with this compound here and we oxidize it, so this would be an oxidation state of 0. We're going to add one oxygen to this, so now we have an oxidation state of +1. If we have a compound like this right here, so this would actually have an oxidation state of 2, because again, this is indicating we're going to think of it as kind of something like this, right? So we would have 2 sigma bonds with oxygen. So this would be a +2 oxidation state. If we have something like this would be this kind of looks funky. That would be a +3 oxidation state. So we can think of it like this. And then lastly, if we have something like this, we would consider this to be either like this. So both of those would have a +4 oxidation state. So again, remember we're counting each bond. So we have 1, 2, 3, 4, or we can look at it this way, 1, 2, 3, 4. So either way, oxidation state would be +4 in this case. So there is an oxidation reduction handout if you want to look into more details when we're looking at the oxidation states. So if we go in the forward direction, these are all oxidation processes. If we go in the reverse, so starting with CO2, these are going to be reduction processes. So let's look at some oxidation of alcohols. So we have looked at oxidation. We're going to look at a few more common oxidants. So there's really three main ones that we're going to look at today. So the first one is going to be PCC. It's usually abbreviated like this. It's pyridium chlorochromate, and the chemical structure of this, which again, you don't have to draw this chemical structure ever. So don't try to memorize how to write this. You can just write PCC, or PCC would be given to you. So again, this is PCC. So PCC is a limited oxidation of alcohols. So this is going to be mild. So we can oxidize alcohols to ketones and aldehydes using PCC. So again, this is going to be mild. PCC, so one downside of using PCC is that it's relatively hard to make, and it involves chromium reagents that are quite hazardous. So that's definitely a downside of using PCC, again, as that mild oxidant. So a couple other common oxidants that we have are going to be the Jones reagent. Jones reagent is also written as chromium trioxide in sulfuric acid. Another one that is common is going to be sodium dichromate. Again, this is going to be in sulfuric acid. So these ones, Jones reagent and sodium dichromate, these are both going to be strong oxidants. So since these are strong oxidants, they can oxidize alcohols to the highest oxidation state possible. So what happens is sodium chromate, or the chromium trioxide, is in a mixture of sulfuric acid and water. So what's used is the in situ, because if we look at chromic acid, so this is chromic acid right here. So chromic acid is very unstable. So again, that's why the in situ of either chromium trioxide or sodium dichromate and sulfuric acid is used. So downside of this reaction also is that this is very toxic and corrosive. So again, really safe handling has to occur when you're using either PCC or Jones reagent and sodium dichromate. So let's look at a few examples of oxidation of alcohols. So if we look at this first example. So let's use PCC. Common solvent here is going to be dichloromethane. So solubility is really good for these types of reactions when using PCC and dichloromethane. So what we have to think about is, okay, we have an alcohol, we see PCC, so that means we're going to oxidize it. So we can only oxidize once. So we are going to produce a ketone. So there's no further oxidation that can occur, again, because PCC is a mild oxidant. If we look at another example with oxidation with PCC, so let's look at something like this. We see PCC with dichloromethane. So what's going to happen, again, numbering may help with these. So on carbon 4, we're going to put a carbonyl, which is going to be converted to an aldehyde because we have a hydrogen coming off of here. So we're going to see something that looks like this. So 1, 2, 3, 4. You don't really have to show the hydrogen coming off carbon 4 if you don't want to. So what happens after this process is basically nothing, because we can't have further oxidation because PCC is a mild oxidant, so we cannot oxidize the aldehyde or a ketone any further. So let's look at an example with Jones reagent. So we'll look at the same starting alcohol. So we'll use Jones reagent, so chromium trioxide with sulfuric acid. So remember, it's kind of an in situ process. So what we would produce would be this product here. So a way to think about this is, let's think of the intermediate. So the intermediate is actually going to be this aldehyde, right? So again, 1, 2, 3, 4. So on carbon 4, we're producing that carbonyl. So when we have Jones reagent, this is going to achieve the highest oxidation possible because it's a strong oxidant. So that means that on carbon 4, we can convert this aldehyde into a carboxylic acid. Let's look at one more example with a strong oxidant. So if we have something like this right here. So we have, let's this time use sodium dichromate. Again, we need sulfuric acid. So we think, okay, we see sodium dichromate. That means this is going to be a strong oxidant. That means we can oxidize everything to the highest state possible. So you also have to think about kind of like your common sense knowledge that you've learned up to this point. So looking at this alcohol here, there's really nothing we can do when there's an alcohol on a tertiary carbon because we can't form a additional carbon-oxygen bond because then we would exceed the octet for that carbon. So really this tertiary carbon right here, we have to leave as is. So then we can work with this alcohol right here. So we can convert this into a carbonyl. And then when we work with this, and we can't go any further because again, we have to think it wouldn't make sense with octet rules. So then when we're looking at this group right here, so with this group here, we can convert this to a carboxylic acid. Again, we can convert it because that's going to be its highest oxidation state. So again, as you're doing these, when you have a strong oxidant, yes, they can go as far as possible, but it has to make sense chemically. So you can't just put tons of bonds on a carbon. All right, let's look at some substitution reactions. So this is actually going to be all review, this last part of today's lecture. So when we look at substitution reactions, we've talked about this several times, that when we have alcohols, so these are bad leaving groups. So they're bad leaving groups, remember, because these are going to be a strong base, but we can convert it to a good leaving group under several conditions. So like I said, you guys have actually done this quite a bit. So we have protonation, and then we can have substitution. So let's look at just like a generic. So if we have something like this, so we have some nucleophile with a hydrogen on it. So most of the times these reactions are going to work with hydroiodic acid, hydrobromic acid, or hydrochloric acid because the halides are strong nucleophiles but weak bases. So the mechanism, if it's going to be SN1 or SN2, depends on the substrate structure. SN1 will usually be accompanied by E1, which you know now from covering chapters 6 and 7. So again, just kind of a general scheme, what's going to happen is we're going to have protonation of our OH, so this OH here, because this is bad leaving group. So now we can make this a good leaving group. So the nucleophile is going to come in and attack here as the group is leaving, and this will give us our product, plus we would have some water. So let's look at it with some actual examples. It's probably actually easier to look at examples than a general scheme. So let's look at this example right here in hydrochloric acid. So what would happen is we would have, so this is where you have to think, is it going to be SN1? Is it going to be SN2? Because that will help you with like retention and inversion products. So we would have this retention product and we would also have this inversion product right here. So these are our substitution reactions or products, and then we would have all our E1 products because again, SN1 and E1 most of the time compete with each other. So E1 products would look like this plus. So you can see that these types of reactions are going to be carried through chapter 10 and 11 too, but it seems by from the quizzes, the last couple quizzes. Everyone is understanding these really well. So these would be our E1 products. So what happens is we're going to have the loss of water. So we're going to kind of steal this proton here. Then we're going to have Cl minus in solution. So we're going to have formation of carbocation. After the formation of that carbocation, again, we have our nucleophile, in this case is chlorine, and it's going to attack at the carbocation site for both the front side and back side attack. So these are both SN1 reactions, like I said. If we look at another type of example, so let's look at this here. So this time we'll look at hydrobromic acid. So really with hydrobromic acid, same exact idea. So what happens is we have H plus, Br minus, right? Because remember, these strong acids fully dissociate in solution. So that's why this is possible. So our kind of, what's going to happen next is we're going to protonate this oxygen here. So this is going to take this proton, right? These electrons would go here. So we're going to have something that looks like this. So this bromine right here is going to come in and attack this carbon as this group is leaving, which would give us this bromine on this primary carbon here. So again, this is a weak base, but it's going to be a good nucleophile just because this would probably precede SN2 because SN1 really can't proceed on a primary carbon without the ability of a like alkyl shift, right? Or a resonance or something like that. So here, technically, we could have a hydride shift also. I guess that would be a possibility, right? So if this group leaves, we have this on a primary, but we do have two hydrogens here. So if we have a hydride shift, we can put our carbocation on the secondary carbon. So if you showed it that way, then it would work SN1. So again, the last part of today you really have seen, I think, in chapter 6 and 7, or you should have seen it in chapter 6 and 7. So really the new things coming from today are going to be the common oxidants that we're going to use. So we have PCC. So again, PCC is going to be mild. It will only oxidize to either an aldehyde or a ketone. And then with our strong oxidants, so something like the Jones reagent or that sodium dichromate, those are going to be strong oxidants. With strong oxidants, we can oxidize to its furthest oxidation state. But again, you have to think about like octet rules and things like that. So we can't just bombard carbon with tons of electrons. So look over this material. One of the drill problems is related to looking at all the oxidants we've kind of looked at and reducing agents also. So look at that drill problem. It's kind of putting everything into perspective and helping you look at it comparatively, and then reach out to me with any questions. So actually, I should mention with the next part of chapter 11, there is going to be one section that we will skip, and I will tell you when we get to that section if you're kind of working ahead a little bit. So have a great day, everyone.